I will explain how electromagnetic waves interact with metal objects and how applying a plasma coating can change the way those waves scatter. I will also discuss how we can analyze the behavior using a numerical method called the FCC FDTD method. This is the unveiling of mysteries. FCC FDDT method analysis of plasma coated metal ball scattering. To begin with, electromagnetic scattering is an important concept to many engineering fields, especially in aerospace and radar systems. Whenever electromagnetic waves such as radar signals encounter an object, part of the wave is reflected or scattered in different directions. Understanding how this scattering occurs helps engineers design systems for radar detection, communication, and stealth technologies. In recent years, researchers have explored using plasma coating on metal surfaces to modify or reduce the scattering of electromagnetic waves. So the main motivation behind the study is to understand how plasma coating influences electromagnetic scattering. In aerospace and defense applications, reducing radar visibility is very important. If we can control how electromagnetic waves such as scatter from an object, we can potentially reduce its radar cross section. Plasma coating are interesting because they can observe or redirect electromagnetic energy, which makes them useful for stealth technologies. Before moving further, let's briefly look at some basic concepts. Electromagnetic scattering happens when waves interact with an obstacle. A simple example is a metal sphere. When radar waves hit the spheres, the waves scatter in all directions. Now, if we add a plasma layer around the metal sphere, the situation changes. Plasma has unique electromagnetic properties that can alter the wave behavior, effective reflection, absorption, and transmission. FCC FDDT method overview. To analyze this problem, we use a computational technique known as the finite difference time domination method or FDTD. FDTD is widely used to simulate electromagnetic wave propagation by solving Maxwell's equation in discrete time and space. In this study, we use a modified grid structure called the face-centered cubic grid or FCT grid. This grid arrangement improves numerical accuracy and reduce errors that may occur in conventional grid structures. Yeah. The challenge plasma and electromagnetic interaction. The key problem we are addressing is the scattering behavior of a plasma coated metal sphere. Especially, we want to understand how the presence of plasma changes the scattering pattern compared to an simple metal sphere without coating. Another important question is whether the FDTD method can provide more accurate simulation results compared to traditional FDTD method. The objective of the research are threefold. First, to simulate electromagnetic scattering from a plasma-coated metal sphere using the FCC FDTD technique. Second, to analyze how plasma properties influence the scattering characteristics. And third, to compare the results with conventional simulation methods to evaluate the performance of the FCC FDTD approach. Literature review. Several previous studies have investigated electromagnetic scattering from a coated object. Researchers have analyzed plasma layers around different shapes, including spheres and cylinders, to understand their effect on radar cross sections. However, many earlier works relied on simplified computational models or traditional grid systems. This creates a gap in terms of high accuracy simulation using advanced grid structures such as FCC grid. Mathematical formulation, the FCC FDDT method. The first is the finite difference time domination, a powerful numerical technique that solves a Maxwell's equation directly in the time domain, captures complex dynamic behavior. Second is the frequency dependent convolution FCC. Uh, Extension for efficiently modeling dispersive material like plasma handles frequency varying electromagnetic properties with precision. Third, completing a plasma modeling uh, enables accurate simulation of a time varying inhomogeneous plasma, supports a arbitrary spatial distribution and dynamic interaction. Case studies and impact. The plasma clocking effect. Visual interactions, visualizing the complex reflection and absorption pattern of plasma coated objects. Case study 1. Magnetized plasma coating. Researchers focus analysis of conductive targets coated with inhomogeneous time varying magnetized plasma layers. Finding is a significant reduction in ballistic scattering radar cross section BCS. Confirmed plasma stealth effectiveness. Parameter optimization dramatically analyzes performance. Analyzing on the FCC FDDT method of electromagnetic scattering characteristic for metal ball coated with plasma. Now, this is the second case study simulating plasma trails. In this, there are three simulation setup, FDDT simulation of electromagnetic radiation, scattering of Gaussian plasma balls, represent the atmosphere, re-entry vehicles. The second is the background fields, comprehensive exploration of how external magnetic field influence scattering characteristic and radar signature. Real world relevance, direct application to spacecraft re-entry scenarios uh, crucial for hypersonic vehicle detection challenges. Fifth is the validation application and future. Quantity stealth, radar cross section RCS reduction. Uh, in this, RCS values for plasma coated spheres under varying conditions reveal dramatic signature reduction potential. Validation and application areas. Technical validation. Computational results are validated against an analytic solution for complex plasma structure. Ensures accuracy and reliability on analyze on the FCC ability method of electromagnetic scattering characteristics for metal ball coated with plasma. And second is radar detection. Understanding interference mechanisms enables improved radar system design, supports countermeasure development. So, third is the communication system. Analyzes radio wave propagation through plasma layers informs satellite and atmosphere communication strategies. The future of plasma scattering analysis. The the future of plasma scattering analysis, robust framework, FCC FDDT method provide a validated computational foundation and model refinement. Continued research improves accuracy and efficiency of plasma scattering models. Expanded application benefits aerospace, defense, and telecommunications sectors opens new frontiers in electromagnetic scattering prediction and enabling next generation stealth technology. Thank you.